Okay, in the previous lecture, we started the double null injection theorem, which we use to find out or derive the closed loop transfer function of a circuit. So in this section, we are going to show you how can we derive the double null injection and the feedback theorem. So first, let's use a block diagram to serve as the case study. So we have the input, right, UIS on the left-hand side, and this UIS goes to a block. And the block has a gain, right? Then this goes to the calculator to calculate the difference between the input signal and the feedback signal. So the output will be the error signal. So UE. And then we go to the block A, right? Block A. So block A can be considered as a controlled current source. The input is the error signal, and here is the control source. And then we have the block B. So here is output. And this is the feedback pulse. So this is a typical negative feedback system. So we want to apply the feedback theorem, right? So the first step is we should locate the injection point. So if you still remember, we have two rules to specify the injection point, right? One is that the UI should be proportional to the error signal, right? Second principle is that the injection point should be a masked pulse from the error to output. So accordingly, in this diagram, the optimal point to inject the signal should be in the middle of those two stages. So here we inject a current source. We denote as IZ to the negative feedback system. And here is we denote as the IX. And here we denote as IY. The positive polarity direction of the current is to the left. So it means that if we denote the positive direction to the right, then IY will be minus IY, right? So it is in agreement with our previous denotion of the system. So based on such a block diagram, we can try to derive those parameters. So first parameter we care about is the original condition. Original condition means that we do not inject the UZ, right, without of UZ. Here, UZ is the current, so UZ is IZ. Then we can define the transfer function G. So G will be equal to the ratio between output, right? Given the condition that there is no injection of the UZ. So UZ equals to 0. So the output signal will be G times input signal. Actually, for a current source, if we consider a current source is 0, means that the current source is open circuit. And based on the original condition, we can still define another transfer function, which is the transfer function of this stage. So we denote this as GA. block A, right? So we define GA means the IY over UE, right? Or over the input signal. So IX, given the condition that UZ equals to 0, equals to minus IY, UZ equals to 0. According to the formula, we can see that the GA is defined as the gain from the input signal to the like IY here, UY here. So which is the gain from the input to here, okay, here to here. Okay, the second step is we can inject the UZ signal. Means that the IZ here no longer equals to 0, right? So for the second step, we consider that the input signal is 0. So there is only one small signal injection is from the injection point. So based on this condition, we can define the loop gain. TS. So TS can be calculated in this formula, right? So IY, given the condition that the UI equals to 0, should be equal to the loop gain, right? So times the IX, given the condition that input is 0. And meanwhile, based on the calc of current law, at this node, we can see that IX plus IY equals to IZ. So combining those two formulas, we can derive that IX UI equals to 0 equals to 1 over 1 plus T times IZ. And IY can also be solved. So which equals to loop gain over 1 plus T times IZ. Okay, those are the two steps. It's like first step, we only consider the impact of the input signal without UZ. Second step is that we only consider the impact of UZ without UI. So next step, we can combine them together using the principle of the superposition, right? Meanwhile, we still have a block here, right? So we can define another parameter as GB. So probably I can put it here. Define GB. So where GB is the ratio between the output signal and the input signal of this block. So here is GB. So we can write the formula, right? UO, given the condition that UI equals to 0, equals to GB times the input of this block, which is IX, given the condition that UI equals to 0. Then GB can also be solved based on the relationships here, right? Because Ix equals to this, right? So UO will be equals to GB divided by 1 plus T times IZ. Okay, that's the GB definition. So next, we are going to consider them together, right? So one is original condition without injection of UZ. One is the injection of UZ without UI. So the intuition tells us that we can basically apply the superposition law to calculate the joint efforts of both inputs, right? So thirdly, in the presence of both small signal input UI and the injection of UZ, so we can apply superposition. So each signal of Ix, Iy, and Uout contains two parts. For example, signal X will contain two parts, superposition, right? First part is given the condition that only we have UI exists, so Iz equals to 0, plus second part is Ix in the condition that the input UI equals to 0. And we can add them together, right? So Ix is here with UZ equals to 0. Ix with UI equals 0 equals to here. So adding them together by superposition. So GA times UI plus 1 over 1 plus T times Iz. And secondly, we can list the expression for Iy by superposition. So Iy with condition that injection is 0 plus Iy in the condition that Ui equals to 0. So similarly, this is minus GA Ui plus T over 1 plus T Iz. And next will be UO, output signal, right? So output signal also can be decoded into two parts in the condition Iz equals to 0 plus UO in the condition Ui equals to 0. So this equals to GUI. And this part equals to GB over 1 plus T Iz. Till now, we have fully expressed those three signals by the principle of superposition. Okay, then the next step is that we do the trick of null, right? So we first null the Iy, step 4. So Iy is here. So we null Iy to 0, right? So on the left-hand side, we just replace Iy to be 0. And on the right-hand side, we just copy this part. So since we know Iy to 0, we mark in the signal in the formula here as the Iy now to 0. And then we care about the formula of U0 under the condition of Iy now to 0. So U0, if Iy is now to 0. Then we rewrite the formula here, right? So this will be G times Ui plus Gb over 1 plus T times Iz, given the condition that Iy now to 0. Then we can combine those two, right? Combine those two. Then we can solve the expression for UO, given the condition that Iy now to 0. Equals 2. So this Iz can be replaced by this part, right? So then this will be time GUI plus GA times GB divided by T times UI. So that's the expression for output signal in the condition that Iy is now to 0, right? Then we can introduce another parameter as G infinity, right? So we define G infinity. So basically, we have defined G infinity, right? G infinity, if you still remember, it equals to UO given the condition that Iy now to 0 divided by Ui. So by combining those two formulas, we can easily calculate the expression for G infinity. So basically, you will see that G infinity equals to these coefficients, right? Coefficients, because the right-hand side contains a common term, which is Ui. G plus Ga times Gb divided by T. And also, we can simplify this formula, right? So then, by introducing G infinity, so then UO, given condition that Iy now to 0, equals to G infinity times Ui, right? So that's the procedure of how we can derive the coefficients of G infinity. Okay, now let's erase the blackboard. Okay, we have erased the blackboard. Previously, we have derived the expression for G infinity. Now let's try to derive the expression for G0. So in order to obtain G0, we need to do the step 5, which we know the Ix to be 0. So then we can rewrite the group of equations correspondingly, right? So if we know Ix to be 0, then we put the Ix left-hand side to be 0. Right-hand side will be the same, right? So remember, the previously Ix equals to Ga times Ui plus 1 over 1 plus T Iz, given the condition that Ix now to 0. And the secondary equation can also be rewritten. So you output given the condition that Ix now to 0 equals to G times Ui plus GB over 1 plus loop gain T times Iz, given the condition that Ix now to 0. So by combining those two formulas, we can derive that the U output, right? U output can be represented by this part, and Iz replaced by formula 1. So U output equals to GUI minus GA GB times UI, which is pretty simple, right? So remember, we previously defined a parameter which is G0, right? G0. G0 is defined as the ratio between the output signal and the input signal. Given the condition that the injection source, now the Ix to be 0. Then we look at this formula, right? So it's easy to extract this ratio. So you will see that this ratio becomes the common coefficients of Ui on the right-hand side, which is G plus minus GA GB. So that is how we derive the G0, right? The closed loop forward gain with 0 loop gain. Okay. Then step 6, we need to know another parameter, which is the output signal. Now U0 to be 0. So similarly, we replace U0 on the left-hand side by 0, meaning that we know it to 0. And on the right-hand side, we keep our original expression as G times Ui plus GB over 1 plus T injection source of Iz, given the condition that output signal is not to 0. And for the expression of Ix, we just write as it is, but we give the condition, right? UO now to 0. So equals to GA times UI plus 1 over 1 plus T times Iz. So the expression for Iy can also be rewritten given the now U0 condition. So this equals to minus GA times UI plus T over 1 plus T times Iz, given the condition UO is now to 0. Then we can combine those three formulas so that we can obtain the expression for Iy by eliminating the Iz and Ui, only keeping the Ix. So basically, Iy U0 null to 0 equals to, I will put the combined coefficients together. So the numerator is t times g plus the product of GA and GB. The denominator is g minus the product of GA, GB times Ix with UO null to 0. So based on this formula, we can define, right? Again, we can define the null loop gain. Remember, right? Tn. The null loop gain is defined as the ratio between Iy and Ix. So Iy divided by X, given the condition that the output is null to 0. So this is null loop gain, Tn. From the resulting formula here, we can easily derive the expression for Tn as these coefficient here, right? Tg plus Ga, Gb over G minus Ga, Gb. Okay, so till now we have derived the expression for Go, Tn, and in the last page we have derived G infinity. So I will rewrite it here. G infinity equals to G plus fraction of Ga, Gb product divided by loop gain T. So those three formulas, 1, 2, 3. By combining those three formulas, we can solve the expression for G, right? So G will be equal to G infinity times a fraction of 1 plus 1 over null loop gain divided by 1 plus 1 over original loop gain. Then we can decompose this fraction into two parts. So you will see that the first part will be this part, G infinity, divided by this denominator, right? We place t to the top, then this becomes t over 1 plus t. The second part is this part, right? This part is G0 times 1 over 1 plus t. See that this conclusion will prove the previous argument we made, right? So the overall transfer function can be decoded by two parts. One is G infinity part, one is G0 parts. So if we look at this resulting formula for the G, right, you will see that G infinity and G0 are critical. So we can try to explain its physical meanings here, right? First, if we consider that the loop gain T is very, very large. For T loop gain, let's say, goes to infinity, then this fraction will be approximately equal to 1. This is 0, right? So G will be approaching G infinity. So this means that the physical meaning for G infinity is that the closed loop forward gain with very large loop gain. large loop gain T. And similarly, if we look at G0, right? So we consider if the loop gain is very small. For T approaching to 0, very small, then this fraction will be equals to 0. And this fraction will be equals to unity 1. So G will approach G0. So this means that G0 can be treated as the closed loop forward gain with 0 loop gain, right? Closed loop forward gain. With 0 loop gain, T. So that's the physical meaning for G infinity and G0. Okay, so in this section, we have fully explained the derivation process of the fundamental feedback theorem. And next, we are going to try to use this theorem in a practical circuit design.